Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to answer a couple questions. Question number one I'd like to chat about here is, what is a conservative force? And question number two, how are potential energy terms derived? So before we can even talk about potential energy terms, again, we got to talk about what is a conservative force. So I've got a picture of Donald Trump here. And we've got the 2016 elections coming up, so this is kind of in honor of Mr. Trump. And Mr. Trump's got this cup of coffee here, and it's a pretty big cup of coffee. You know, he likes his coffee, so do I. And we're going to imagine here that Mr. Trump throws that coffee cup up in the air so that the cup basically does this, up to a certain height and back down again. And I've got a picture of the cup and a little bit of his hand here by mistake, but I've got a picture of his cup at this position. The cup moves up to this position and then back down again. Now I'm going to give this height here a certain name. Let's just call that height h. Now what the actual number is does not matter. Now I'm going to talk about a free body diagram of the cup. What does a free body look like? So while the cup is in the air, there's really just one force acting on it. That force is down, and that's the force we call the gravitational force, mg. And what we're going to do here is we're going to look at the trip on its way up and on its way down, and we're going to look at the work done by the gravitational force. So while we're on the way up, the work done by the gravitational force is going to equal, now if you don't know how to calculate work, I suggest you go back and look at my videos on work calculations. Work is force times distance, but the force has to be parallel to the motion. And there's a plus and minus sign that's very important for this video. Work is positive when the force is in the direction of motion. Work is negative when it's in the opposite direction. So in this example, the force is the gravitational force, mg. The distance is what I have labeled as h. And the work done as the cup moves from the bottom position to the top position would be negative because the force is down but the displacement is up. Okay. On the way down, the work done is, well, force is mg, the distance again is h, except on the way down, the force is in the direction of motion, so the work is positive. The net work done is the sum of the two, which is 0. Now, this is kind of an overly simplified version, but this is a property of conservative forces. The gravitational force is an example of what's called a conservative force. And there's a couple mathematical descriptions of conservative force. I'll give a very simple one. If you look at an object or some sort of system and you look at it for any closed loop, now in this example this is one-dimensional, up and back down, but it doesn't have to be. That cup could have started here and did any number of different paths back to where it started. If the net work is 0 for any closed path, then that force is considered a conservative force. So this is what I mean by closed path. If you start and you end at the same point, so this cup started here, went up, came back down, ended at the same point, that's what I mean by closed path. This was a one-dimensional example, but it doesn't have to be. Had the cup did anything like this, crazily, as long as it ends up back at the same spot, the net work done by gravity will in fact be 0, and that's one of the mathematical properties that makes gravity a conservative force. I like to kind of give a little more of an ad hoc definition in terms of how conservative forces affect the energy state of a system. Conservative forces do not increase the energy of a system. When this cup was on its way up, it had a certain kinetic energy. When we get to the highest point, that energy is still there. The evidence that it's still there is later on when the cup falls back down, it goes through this position with the same kinetic energy it had before. So the energy at this state basically is the same. We say that the cup has a potential energy at this position. Let's compare that to a different example. Where's my favorite race car here? Well, we'll just take this one. All right, so imagine this car is moving down the road and it stops via its brakes. When we look at a free body, we would have a normal force up, a gravitational force down, and a frictional force to the left. So there's the frictional force, there's the gravitational force, there's the normal force. And again, so this was for a car moving left to right, applying its brakes. The normal's not doing any work, neither is the mg. There is work done by friction. Notice, though, that if this car did some sort of complete, or let me back up. Notice that when the car stops, the kinetic energy of the car has dropped, the potential energy is the same, and the total energy of the system has changed. Friction is an example of a non-conservative force. If I go back to this definition here, where net force is 0 for a closed path, imagine that this car gives it the gas. What that would do is it would reverse the frictional force direction. Now the frictional force is this way. And imagine that the car did that and accelerated the entire time and somehow did a closed loop, meaning that it did and back to where it was. If that frictional force stays constant and in this direction, when the car gets back to where it started from, it's going to have a massive speed and massive kinetic energy. So the net work done is now some positive value. So friction is an example of a non-conservative force. Get rid of the stuff I don't need anymore. Gravity is an example of what's called a conservative force. Whoops. Now, the next question is, what do we do with conservative forces? Well, here's what we do. We derive potential energy terms for them. So when I look at this example right here, I'm going to go ahead and put a coordinate system into the problem. And I'm going to put it down here. Just right, whoops, right here. X, Y. Now, in this example, the cup's x coordinate isn't changing, just the y coordinate. And what I'm going to do here is I'm going to imagine this cup starting at this position and falling to this position. And we're going to do some quick little calculations here. I'm going to do them right here. Here's how potential energies are determined. The change in potential energy is equal to the opposite of the work done by the conservative force. So in this example, if we start here, if I call this position 1 and this position 2, and we look at the work done by the gravitational force, the force is mg, and in terms of y now, we've got a y1 and a y2. And this distance h would be y1 minus y2. So the distance I'm going to put here is going to be y1 minus y2. So the force mg, distance h, this term is the work term for the gravitational force as it moves from 1 to 2, and it would be positive because the force is down and the displacement is down. And that's equal to the change in potential energy for the cup. Now you notice that by the time I distribute this minus sign, we end up with mgy2 minus mgy1. Because this minus sign hits this, minus mg times y1 would be minus mgy1. And minus mg times a minus y2 gives us positive mgy2. So we've got this expression, mgy2 minus mgy1 equals the change in potential energy of the cup. Therefore, these are potential energy terms. This is the term I would call PE2. This is the term I would call PE1. And the expression mgy is what's called the gravitational potential energy of a system. Now, there's a lot of assumptions that went into this. This equation is really only good where we're talking about constant gravitational fields. So this equation is good at the surface of the Earth, anywhere at the surface of the Earth, and that g is about 9.8 meter per second squared. If we were on the moon or someplace else, we'd have a different value for g. Or if this height varied far enough that we couldn't consider gravity to be constant, then the math gets a little bit more complex. But I think for this video, that's good enough. As far as what is a conservative force, mathematically, it's a force where if you start at a position and you go through a series of displacements, but you end up at the same position and the net work is zero, then the force is a conservative force. I like to say this, it's a force that doesn't change the net energy of the system. It doesn't increase or decrease the net energy of the system. Now, what can we do with conservative forces? We can define potential energy terms for them. How do we do that? From here, the change in potential energy of a system is equal to the opposite of the work done by the force. This can be used to find potential energy terms for gravity, whether gravity is constant or not. However, if it's not constant, it requires a little bit more math. And if you're going to have me for physics, second semester physics and spring semester, we'll be using this to derive potential energy terms for what's called the Coulomb force. Anyway, I hope that this video helps answer these questions. Have a great day.